Well, hello folks. And today we're going to be looking at the first part of the refraction of light section in higher physics. And first thing we need to understand is what is refraction? So as you can see here, we have a beam passing through a perspex block. And the red light, or the red lines, they represent the crests of the light wave. And the black line represents the actual ray itself. Now, if we look at it, we might remember from National 5, in fact, that when light moves from a less dense material, like air, into a more dense material, like perspex, then firstly, the light slows down. And you can see these red lines slowing down when they enter the perspex. And when that happens, because one wave slows down, but the one behind it keeps going for a little while, it sort of catches up, and therefore the wavelength decreases. And also, because the bottom bit of the wave is catching on the block first, it's almost as if it trips over and it falls forward. So the direction of the beam changes as well, and it bends towards the normal. One thing that doesn't happen, though, is that the frequency doesn't change. Remember, frequency is the number of waves per second. So although the waves are getting closer together, they're also slowing down by the same proportion. So the number of waves per second inside the block is the same as outside the block. So the frequency remains constant. And then as it leaves, you can see the wave speeds up again. And because one wave leaves first, it accelerates away from the one behind it. So the wavelength increases again. And the direction changes the opposite way this time, and it bends away from the normal. But again, the frequency doesn't change. Now, the extent to which this happens, the extent to which the light slows down and speeds up, the extent to which its wavelength decreases and increases, and the extent to which the direction changes, all depends on the optical density of the material. And that's measured using a term known as the refractive index, which has the symbol N. Now, we're going to talk about an experiment where we could measure refractive index. So what we would maybe do is we would set up the experiment a bit like this, where we've got light shining into the flat side of a semicircular perspex block here, and then leaving through the curved surface. And we could measure the angle that the light makes with the normal in the air and call that θ1. And we could measure the angle the light makes with the normal inside the perspex, and we'll call that θ2. And then we could draw a graph of various θ1s against θ2s. And we get a graph that looks a little bit like this. So sine θ1 against sine θ2 gives us a straight line through the origin like so. That tells me that the sine of the angle in air, θ1, is directly proportional to the sine of the angle in the material, θ2. If it's directly proportional, that means we've got a constant gradient, and indeed the gradient in this case is equal to the refractive index of that material. So we can write it like this: N equals sine θ1 divided by sine θ2. N is the refractive index. θ1 is always the angle in the air, regardless what direction the light is traveling. And θ2 is always the angle in the material, regardless of the direction the light is traveling. So, ratio of sine θ1 to sine θ2 is equal to the refractive index. Key points to note. Firstly, the refractive index is always greater than 1. You'll never get a refractive index that is 0 point something. The reason for that is that a vacuum, or air, has a refractive index of 1. If we had a refractive index less than 1, that would mean that the light would speed up as it entered that material. Now, there is no possibility of light travelling faster than the speed of light in a vacuum. So it's not possible to have a refractive index less than 1. So the refractive index will always be more than 1. Theta 1 is always the angle in the air, theta 2 is always the angle in the material, regardless of the directional way the light is travelling. And lastly, theta 1 is always larger than theta 2. The angle in air is always bigger than the angle in the material. So here's a little example for us. A ray of red light is instant on a glass block as shown. The refractive index of the glass for this light is... So we can see the red light entering through the air and then getting into the glass. And we've got various angles drawn on our diagram here. Now, refractive index is sine theta 1 divided by sine theta 2. Theta 1 is always the angle in the air, and we must always measure our angle between the light ray and the normal. So theta 1 in this case is 30 degrees. Theta 2 is the angle within the material. And again, we must always measure it between the normal and the light ray. So in this case, the angle is 20 degrees. So the refractive index is sine 30 divided by sine 20, which is 1.46. One thing to be aware of, if you are also studying higher physics, higher maths at the same time as studying higher physics, you might be learning about radians. If your calculator is set in radians, then you'll get some sort of crazy answer here. So make sure whenever you're in physics, your calculator is set in degrees. Now, actually, it's not just the angle that's changing, as we mentioned, it's the speed and the wavelength that's changing as well. And actually, the speed and the wavelength change by the same factor, the same refractive index factor. So we can extend that formula, n equals sine theta 1 over sine theta 2, to equal v1 divided by v2, which is the speed of light in air divided by the speed of light in the material. And that's also going to be equal to lambda 1 over lambda 2, which is the wavelength of light in air, divided by the wavelength of light in material. So n sine theta 1 over sine theta 2, v1 over v2, and lambda 1 over lambda 2 are the same value. So here's another example. A ray of blue light passes from air into a transparent block is shown. The speed of light in the block is... So here we can see the change in direction of the light ray, but we want to know what the speed of light would be in the block. So we have this big combined formula. N equals sine theta 1 over sine theta 2 equals v1 over v2 equals lambda 1 over lambda 2. So the refractive index is equal to sine theta 1 over sine theta 2, but also equal to v1 over v2. We can ignore the wavelength bit in this case. So we could do this in one quick bit and just do sine theta 1 over sine theta 2 equals v1 over v2, or we can be a little bit cautious and work out the refractive index and then work out the speed second. And that's what I'm going to do. So I'm going to start with n equals sine theta 1 over sine theta 2. Theta 1, remember, is the angle that the light ray makes with the normal in air, which is 60 degrees in this case. Theta 2 is the angle that the light ray makes with the normal in the material, 40 degrees in this case. So I can measure my refractive index, sine 60 divided by sine 40, which is 1.34. Now, my refractive index is equal to v1 over v2. v1 is the speed of light in air. I know that is 3 times 10 to the power of 8 meters per second. v2 is the speed of light in the material. That's what I'm interested in. So I can put my numbers in there. N is 1.34, which I just worked out. v1, 3 times 10 to the power of 8 over v2. A little bit of rearranging, and we get the speed of light in the material to be 2.2 times 10 to the power of 8 meters per second. So that's how we deal with the refraction at higher physics. In the next video, we're going to look at a special case of refraction known as total internal reflection and the critical angle. But until then, thank you for listening, and I'll talk to you again after a while. Bye for now.